All right, so my name is Shailesh. I'm going to talk about a topic called reasoning. And what we'll do in this talk is sort of contrast it with prediction, which is what a lot of talks and a lot of machine learning that you've seen today and in your work is really a different kind of machine learning, which is mostly prediction kind of machine learning. So we'll talk about another kind of machine learning, reasoning, which is what we do as well as we do prediction. And really what I want to do is show when your problem is really a prediction problem, when is it a reasoning problem, and if it's a reasoning problem, what are the things you can do with it, right? So that's the broad theme. So let me start with something I talked about last year, which is, if you think about where is AI going, and there are a lot of speculations these days whether it's going to kill humanity or it's going to redeem humanity. We don't know which way it is going, but I'm going to talk about it from a very simple perspective, which is there are a lot of things that we call AI today, right? So a lot of companies are using AI, and it has become a very big buzzword for a lot of things. So let me just separate out a bunch of other things within AI. So obviously, the first thing we do is we do a lot of learning. We learn the n-grams, we learn the prediction model. So there's a lot of that goes on, which is AI. Then we do understanding. So if you look at word embeddings or image understanding and things like that, we do a lot of semantics, right? Word sense disambiguation. So that is another kind of AI, if you will. Then the third kind is what we call thinking or reasoning. And we're going to spend a lot more time on this one today. What is thinking? And I'm going to talk about thinking 2.0 because last time I promised we did thinking 1.0, so today we'll do thinking 2.0. And what is creativity? Obviously, there's a lot of philosophy around it. And finally, what is consciousness? And if we get time at the end, we'll watch a video about this. But the idea is those top two are still in the realm of philosophy and metaphysics, but these three are something that we are actually doing. So, we've all seen a lot of things in this realm. I want to focus a little bit on what is reasoning and thinking. If you want to keep thinking about data science, there's another way to think about it, that we are going through a transition right now from pure data science, the way we understand it, and AI, which is kind of the all-consuming. And I talked about this the last time, which is unless we keep sticking with language, and the idea that there is something called language, we are not going to make the leap to the next thing. We need to start getting away from language towards knowledge, because really the purpose of language is to communicate and store and transfer knowledge. And knowledge is the essence. Language is just one form of knowledge representation, right? So this is one thing we talked about. Second, a lot of things going from tokens to embeddings now. So if you look at the old world, we used to do TF-IDF. In the new world, we all do word embeddings and vector embeddings. So we are going from tokens to embeddings. And the third thing we are doing is we are also going to go from prediction to reasoning. And I'm going to make that distinction today, which is what is prediction versus reasoning, and where do we apply reasoning. All right, so let's look at a set of tasks that we all do in our jobs, right? So let's say I have a task of predicting whether this transaction is a fraud, or whether these coupons should be sent to those customers, or whether this job is relevant to this resume, or vice versa. Whether what are the objects in this image? Is there a hacking going on into my cloud system or my other systems? This has become very popular these days. And whether this customer is about to churn. And all these problems have a very, very specific, very, very same type of sort of structure to it. And these are all what we call prediction problems. The idea is you're given some input and you have to predict something. And there's a whole variety of these problems that you can think of. It doesn't depend on what kind of data you have. It doesn't depend on what you're trying to predict. I'm not making distinction between classification and regression or those things. I'm saying all these are prediction problems. Right? And obviously, if you look at how prediction has evolved, it has evolved from, since the early childhood, if you will. We all started with the basics, and then we had neural networks and kernel machines and support vector machines and random forest and things like that. And today we are doing something even more interesting. We are doing deep learning and graphical models and XGBoost, right? So there's a long history of where prediction is, and it has evolved into a very, very complex thing because we have put so much effort into building prediction models all the time, right? And we use this to do very, very complex tasks now, but it is still the same paradigm. It doesn't matter whether you're driving an old car or a new car, you're still driving. And I want to make that point about the paradigm shift. We are not flying yet in that sense. We are still driving. Our cars have become faster and better, but we are still driving. So it is not a paradigm shift from these guys to these guys. We haven't done a paradigm shift in terms of what do we do in terms of input-output mapping. Right? Now let's look at another class of tasks. These are the tasks that we do very naturally. Machines also do. But I want to make the distinction so it's obvious. So if you look at the task of, for example, finding your shortest path or multiple paths from A to B. So this is Google office in Manhattan. This is the Central Park. And if I say, give me a bike route, it's going to give me 3 paths and so on, right? So we use this all the time. What about the recent games that we have been winning, right? Go, chess, and all that. What about solving math problems, right? When we solve a multi-step math problem, you start with this and you say, okay, what can I do? What can I do? And you keep going and you come to the answer. This is another class of problems. What about conversation? So I'm going to model conversation not as a prediction problem, but is it really a prediction problem, right? And what about diagnosis, or what doctors do to diagnose, right? Or what Sherlock Holmes does to find the clues and solve a mystery. And the task that is closest to most of us is how about crossing a road on a busy street? Okay. Now, what is common between all these tasks? There's something very common between all these tasks, and that's what we are going to talk about. So these are all what we call reasoning problems. They're not prediction problems. They are reasoning problems, and we'll harp on what that distinction is and how do we get there. All right. So reasoning also has been evolving as prediction has been evolving, but now it's a paradigm shift. So now we have started flying, and in the early days you must have heard of the things in A-star search and shortest path and theorem proving and rule-based expert system. They were all designed to do these reasoning tasks, which we'll see what they are. Then came these Markov decision processes or reinforcement learning, Q-learning ideas. I don't see a lot of those things used in our day-to-day efforts today, and hopefully this talk will sort of give us some more ideas around how we can use these ideas into our work. And now we are also talking about deep reasoning or hierarchical reasoning or multi-agent systems, right? So the idea is reasoning is a very different ballgame. It's very different from prediction. It has been evolving the same way prediction has been evolving. And we just need to know when to apply prediction, when to apply reasoning. Okay. So let's look at the differences between prediction and reasoning. So if you look at a prediction paradigm, it's a very simple paradigm. You start with some features that you've created either through feature engineering or statistical things, and then you build a model and it gives you a prediction, right? It's a very simple input-output mapping. And the characteristic of this is that the next data point is independent of the previous data point, right? IID assumption. So you don't have to worry about state in this case, right? A prediction is done, move on, next prediction is done. You can do 1 billion predictions per second today, and they have nothing to do with each other. It's a very simple paradigm, and that's what has led us to this far. And we've been able to do very, very complex things with just this paradigm. What is a reasoning paradigm? How is it very different? Is that it's not a one-time prediction. A reasoning paradigm is really about multiple predictions and trying to figure out after this prediction, what is the next prediction I will do, and then the next prediction I will do, right? So imagine if you start with, let's call it a state, and you say I have 3 choices, and then you take this choice, and then again you have 3 choices, then you take this choice, and so on and so forth. And that is sort of the idea that here you're not doing a mapping between some input to some output, but you're making a series of things, right? So if you look at how Google search finds your path, or how we play a game. Really, it's a sequence of decisions that we make, and it's a very different paradigm, and we'll see how that works. Another interesting thing about reasoning is that in case of prediction, you get an immediate feedback, right? So you make a model while training. As soon as you are done with the output, you get a expected output, and you get an error that you backpropagate, right? So every prediction algorithm does that in some form or the other. But in reasoning, what happens is you don't get a feedback right away, right? You make the first move of chess, you don't know if it is right or wrong. You may move the 10th move in chess, you don't know if it is right or wrong. At the end of the game, you realize, oh, I won or lost, right? Similarly, in other such problems, we make a sequence of decisions, and sometimes only at the end of those sequence, we get a feedback, and then we realize whether we did the right thing or not. And one of the problems is then you start blaming and say, is this the wrong decision? Is this the wrong decision? Is this the wrong decision? Why did I lose the game, right? So that is our difference between prediction and reasoning. Now, there are different flavors of reasoning. Like I said, reasoning has been evolving since a long time. So the very first kind of reasoning was very algorithmic. So this is where all the computer scientists got together and said, okay, we know how to do breadth first search, we know how to do depth first search, we know how to do branch and bound and all that. And now how do we take this forward? And then we came up with A-star search, right? So A-star search was a very important algorithm in AI. And it's an example of what I call algorithmic reasoning. It is a computer science way of doing it. It's not a data science way of doing it, but it gets you the same result. Then, for a very, very long time in the history of humanity, we have been doing logical reasoning, right? So we have predicate calculus and all the calculus, and we do a lot of theorem proving. And there's a lot of theory around how do we do logical reasoning, right? If all birds can fly and this thing is a bird, then can it fly, right? That kind of thing. And we've been doing this for a long time, and this is the foundation. These two algorithms are sort of the foundation of the modern AI, and they are all reasoning algorithms. Another kind of reasoning you can think of is a Bayesian reasoning, which is you're given a bunch of cause and effect relationships, and you want to understand what caused what, and there's a causal structure around it. And a lot of work has happened in graphical models, Bayesian networks. So there you can talk about, if you have fever, what could be the cause, and what should I do with it, right? So you can go backward and you could go forward. And there's a whole bunch of theory on how to take logical reasoning, which is binary, true and false, to probabilistic, which is Bayesian, which is what is the probability of fever versus do you have fever, right? Today, I'm going to talk about two other kinds of reasoning. I call them, this one I call a Markovian reasoning, which is really about the states and actions and, the sequence of actions that we take. Another, broad area is Markov decision processes, which is sort of about this kind of reasoning. And then I'll also talk about reasoning that we do in our brain, related to associations, right, and knowledge graph and things like that. So we'll focus on these two and see what these are and how do we apply them. All right, so let me introduce this notion, the idea of a Markovian reasoning, right? So there are these notions of states, actions, and goals. So I'm going to use several examples in different domains so we really understand these ideas so that we know how to apply them when we have to build our own reasoning systems, right? So if you think about the reasoning problem that shortest path is solving, we have two states. You have a start state and a goal state. So the idea of state is very important. Then you have other states, right? At any given time, you could be here, you could be here, you could be here. So the location on the map where you are at this point is a state. Now, in addition to that, you can say, is it raining? Is it, flooded? Is it blocked, right? That is also part of the state, if you will. So state is anything that you can observe is state. Not anything that you can control, but anything you can observe is a state. Okay, so let's look at actions now. So at any given state, you could do multiple things. You could go here, you could go here, you could go here. So at every state, you can define a set of actions you can take, right? So the idea of states and actions in the map world. And the overall goal, we're not just talking about this goal to reach. We're talking about the overall goal of this whole problem is to reach the destination as safely and quickly as possible, right? So there's this broad idea of the goal. There is this idea of the goal state, start state, actions, and states. Let's look at tic-tac-toe, right? So if you look at a board position on a game, that is also a state. So this is also a state, and then you can, your goal here is to win the game, and obviously you have a bunch of moves that are actions, right? So you could take this action or that action, and again, depending on the right moves or wrong moves, you are going to win or lose. What about mathematics? Again, we have states. So now I'm going to introduce this idea that, let's say I want to solve this equation or expression, simplify it. Again, I'm going to say this is a state. And what are the actions? The actions are the things you can do in the current state, right? That's the action. So here, you cannot do sine square plus cos square equal to 1 identity, because that is not possible, but you could do these things, right? And depending on what you do, you're going to get into new states, right? So that is a very simple paradigm, and therefore it can be expressed in this form, states and actions. All right, and here the goal is to simplify the problem in the minimum number of steps, for example. All right, so let me talk about another completely different kind of thing and see why that is also a reasoning problem. So let's talk about chatbots. So every second or third startup is doing a chatbot today. So let's talk about chatbots. Now, if you look at two kinds of chatbots, I distinguish between two kinds of chatbots. One is what we call a form-filling chatbot. So these guys help you fill a form in the background, and then they submit the form and things get done, right? So if you want to go to fly to US, you talk to your chatbot and say, I need to fly to US, and it's going to ask you a bunch of questions. Ultimately, what it is doing is filling a form which you would have filled at yatra.com or one of these websites, and it's just another interface to fill the form, because we love to type and not click anymore, right? So that's the idea behind what I call form-filling chatbots. So what is the goal in this case? If I want to model this as a reasoning problem, what would be the goal in a form-filling chatbot? Okay? So the goal would be, hey, fill the form accurately, don't assume anything. Fill the form completely, don't miss out anything, and take the minimum number of steps. Don't ask stupid questions and things like that, right? So that is the idea. The goal is defined. What about state? What is the state? The idea of a state in a form-filling situation. So imagine you are filling the form and you are at a certain state. You have not filled certain things, you have filled certain things. Think of that as a state. So here also, if you think about what is the request, so this chatbot can do all kinds of things, right? It can book a cab, it can buy some stuff, it can order food. So what is the request? What is the context? Where are you? Which city you are in, right? Things like that. What is your context? What are your past preferences? Do you like veg food, non-veg food? Do you like aisle versus this seat, right? So these are your past preferences, and the chatbot knows about it. And what is the metadata? What is your credit card number and all that, right? So think of that as a state, and the state is being filled as we go along. And then what are the actions the chatbot can do? The actions are the things that the chatbot can say to you, right? Those are the things he can say to you. And he can say, okay, when do you want to travel? Where do you want to travel? It can also tell you today's weather. But in this conversation, is that a good action? Right? We don't know if this is a good action. Or it can ask you about the movie that you watched yesterday. And say, how was the movie? Right? It's trying to have a conversation, but you're trying to book a flight. So just because you can have an action doesn't mean it's the best action to have. And the real problem with the chatbots that we have to solve is, how do you ask the right questions? How do you pick the right actions so that you meet your goal in the current state? Okay? Now let's talk about another kind of chatbot, which is very different. This is what I call a small talk chatbot, right? It has no goal. It doesn't care about your booking or doing something. It's just a general thing that you talk to. And what is the goal there? You're just having a casual conversation. Exactly. Keep the conversation going. Thank you. I will do that. Right? So basically, this guy is basically saying, keep the conversation going. and keep it interesting, right? Keep it coherent. Don't keep talking about random things. So that's a goal, right? It's a very abstract and a very different kind of goal than the first one. What about the state? How would you define the state of such a conversation? Last thing that you said, okay? Mood, right? So you can think of the state and say, what is the state of the conversation? And you can think of, what is the stage of the conversation? Have we just met, so I should say hello, hi, or has the conversation been going on for a while, so I should say something else, right? What is the stage of the conversation? Am I about to end the conversation, so should I say something else? What about the interest of the other person, right? I'm saying something, and this is what we do in human conversation a lot. We try to gauge the interest of the other person and see if we need to change the subject and things like that. Where has the conversation been so far? What all have we talked about? So we don't talk about the same things again and again, right? And like you said, what is the last utterance? And based on that, I want to make the next utterance. Okay? And again, the actions could be many. So you can say, hey, I could exchange pleasantries, hello, hi, bye. I can make a statement, the weather is great today. Or I could ask a follow-up questions, right? Where do you live, for example? And then I can change the topic depending on whether the interest is there or not, right? So that was one of the goals of, even if you look at the Turing test and those kind of Turing test kind of systems, they're really trying to solve these problems, which is, how do you have a general purpose conversation which has no specific reason and yet be able to keep the conversation going and feel like the other side is a human, right? So this is the real chatbot that we need to build eventually. This is a good stepping stone in that direction. Okay? All right, so let me now ask you, so we understand the idea of what is a state, what is a goal, and what is a action. So now let's talk about the atomic unit of reasoning. I like these questions, atomic unit of something. So what is the atomic unit of reasoning now? What is the simplest atomic thing we do when we do reasoning? Pardon? Thinking, okay. Decision making, okay. Backtracking, okay. If you keep backtracking, then there has to be something forward looking too, right? Yeah, next action, right? So let me put this problem in a different way. So let's say your friend calls you and it says, hey, how do I come there? Right? She says, how do I come there? What is the first question you ask him? Right? And then what do? Then you decide, how do we get here? And he takes a left. That's all. This is the simplest thing that we do when we do reasoning. So the idea is you have a goal, right? I have to come there. And you have a state, where are you now? And then you have to decide what the action is. So this is the building block. If you think about backpropagation, what is the building block? A neuron, think of this unit is the building block of reasoning. So you can build any kind of complex reasoning system by putting a whole bunch of these units together, right? So the real goal is, how do we think about goals and actions? How do we represent them? And then how do we learn this box over time? All right. And the best part about reasoning is that it's not a static thing. Unlike prediction, which is done. Once you're done with the prediction, you're done. What happens here is, once you take an action, it changes your state, and now you have to do it all over again. The goal doesn't change, but your state has changed, so now you put in the new state, and then again you do an action. So now you see how we learn to play chess and Go and bicycle and everything. It's really about this loop. And really, these are the units that we use to build our reasoning engines. Now, let me present a very ethical dilemma. So we talked about state, actions, and goals. Now, we are living in an era of autonomous cars. So one of the recent news around that was that why the self-driving cars must be programmed to kill, right? That means it is okay to kill, should not be there's a threshold to it. You can't just say definitely not kill. And in that article, they show this picture. So the idea is the car is coming, a pedestrian is crossing, and so there is a state. The idea is there is a state. The car can observe the state, and then the car has to take an action, right? Again, a car is coming, a bunch of people are crossing, and again the car has to take an action. But the third figure is where things become blurry, right? And this is where it says, hey, if you take this action, you're going to kill this guy, and you can't turn this side, and you can't stop immediately. What are you going to do? So eventually, our reasoning systems that actually depend on, or on which such things depend on, will have to not only think about states and action in a very simple way, but also incorporate some of these moral dilemmas into them. Okay? So we understand the idea of states, actions, and goals. And now let me talk about Markovian reasoning, what this whole process is. And here, what I'm going to do is I'm going to distinguish between what is knowledge, learning, and reasoning in this context. Okay. So let's go back to tic-tac-toe. The AI researchers' favorite game is tic-tac-toe. We always go back to it. And now, tell me, who tells me what to do next? If I throw a board position in front of you, who tells me what to do next? Not what to do next, but what are my options? How do I know what to play next? So this is the state, right? I'm in this state. I need to win the game, and I need to make a move. So there are two parts to making a move. The first part is I need to know what are my possible moves, right? In optimization, they call it the feasible solutions and the optimal solutions, right? So what are my feasible moves in this state? And that is what we want to know. So who tells me what are my feasible moves? Rules of the game, right? So the rules of the game is the knowledge. In this case, rules of the game is the knowledge, and that only tells me these are the possible moves you can make. It doesn't tell you anything else. Knowledge does not answer the next question, which is the best move. It only answers this question. If you present me a state, I'll tell you what are the possible moves. How about math? What can I do? So if a student is struggling with math, he's looking at this equation, how does the teacher ask him what to do next, right? So the student knows certain things, the student does not know certain things. Based on that knowledge, the student will say, okay, either I could do this, or I could do this, or I could do this. And it depends on the knowledge of the student, right? If the student does not know this formula, he cannot make this as a feasible move. So we understand the idea, the role that knowledge plays. Knowledge is really about enumerating the options. That's all it does, and says, what all can I do at this stage? Now, what about the complexity? I want to define this notion of complexity of knowledge. So we all understand at some intuitive level the idea of complexity of data, right? Data is complex because there's a very difficult decision boundary to learn, right? VC dimensions, all kinds of things you can think of. But the idea is we understand at some level what is complexity in data. We also understand what is complexity in a model, right? The larger the model, the more complex it is. Now, let's answer this question. What is complexity in knowledge? What makes knowledge more complex or less complex? Okay. The more connections, the more alternatives, right? Okay, very good. So I'll give you a very quick anecdotal example. So one day I was watching this movie which had a thing called the extinction level event. So I paused the TV and said to my 8-year-old, hey, do you know how the dinosaurs died? And she said, yeah, I know how the dinosaurs died. And she was about to tell when my 3-year-old came and said, I also know how the dinosaurs died, right? And they always know all the answers, right? 3-year-old, they'll know all the answers. We're talking about knowledge, right? So we all gathered together and we said, what is her interpretation? And so we said, how did the dinosaurs die? And she said, they died like this. Right? And this is simple, right? That's what she does. Simple. So the idea is, depending on the knowledge that you have, you're going to make those kind of answers, right? So a 3-year-old's knowledge versus an 8-year-old will give you a different answer. So that's the idea of complexity. So as we grow, we learn more and more complex things, right? We learn math from so many years to so many years. We learn so many things. In a way, our complexity of the knowledge is growing, right? So what does that really mean in our terms, in in data science terms, if you will. Right? So let me put that question in a very simple way. So let's say if I ask you, which of these three games is most complex? Go. It has more combinations, right? So if you look at these three, I can think of knowledge complexity in multiple ways, right? So I can say, hey, the complexity could be the number of rules, right? How many rules do I have to follow? So if you look at that as an example, then chess has a lot more rules than Go, right? And obviously this guy has very few rules. So the order will be different. Go will be less complex than chess if the number of rules is what thing was, right? So knowledge, the size of the knowledge, if you will, the number of rules, does that make something complex, right? That is one notion of complex. I'm not saying yes or no. Another notion of complex could be the size of the state space. How big or how many possible states the system can have. And obviously this guy can have 2 to the 9 possible states, and but chess and these games can have a very large, right? So that's another notion of complexity, which is how big your state space is. And the third reason that a lot of people talked about is really the branching factor, which is how many options do I have at any stage. So if you look at tic-tac-toe and you look at the first move, there are only 9 options. But if you look at chess, there are 20 options. And those of you who know chess, you can calculate. And in Go, there are 361 options right in the first move. So this is what we call the branching factor. And the branching factor, the higher the branching factor, the more difficult it is to pick from them, right? The more complex the model you will have to build to pick the right action among large number of actions. So there is this notion of complexity of knowledge, and we can look at all these three to think about it. So coming back to knowledge, so the idea of knowledge is obviously if a third grader is solving this problem, maybe he has nothing to do because he doesn't know what to do next, but maybe a fifth grader can apply more knowledge and eighth grader can do it even better, right? So the idea is depending on your knowledge, it can enumerate all the options, but how do we know which one is better? And that is not the job of knowledge. If you think about it, that is the job of what we call learning. So when we are told the rules of the game, do we become a good player of the game? No, right? We still have to learn the next thing, which is how do I make a move among the feasible moves in the current state? Unless I learn that, the knower of the rules is not a grandmaster of the game, right? So how do we learn? So what do we do in tic-tac-toe? We play a lot of games. Sometimes we lose, sometimes we win. And then over a period of time, we figure out that certain actions are better than other actions, right? So that is the idea of learning. And this is what learning does. Learning only quantifies the goodness of a state or the goodness of an action given the current state and the goal, right? So that's what learning does. And the whole, the theory around reinforcement learning and other kinds of learning is really centered around this idea. How do we learn once we know the knowledge? So knowledge only constrains my forward path and says these are the only things you can do. Learning really decides where I go among them. And what does reasoning do? So I'm going to give you a sense of what is reasoning. Reasoning really explores and uses knowledge and learning in a very interesting way. So if I start with this, my knowledge tells me that these are my 3 options. It is the knowledge that tells me, right? But learning, if I've solved many such problems before, and I know which one is going to give the best solution quickly, I will say this is better than these 2. And then I say, okay, now I'm going to take this action, and now what? I am again back to a state. Again, I have to do the same thing. My knowledge tells me you can do these 2. My learning tells me you should do this one. And my knowledge again tells me from here what are the options. And my learning tells me this is a better option. And again, my knowledge tells me these are the 3 options. And my learning tells me that this is really good, right? So we understand the role of knowledge, learning in the process of reasoning. So reasoning is recursively using knowledge and learning in this process. Okay. So now let me give you an architecture of this whole thing. We talked about different things. So the idea is you start with the current state. Anytime you start, you are in a current state. Your knowledge is going to tell you what are the feasible states. Then what do? We take each of the possible actions in our mind. So think about how you learn to play chess. You first take the action in your mind, and then you decide, am I better off or worse off now? And then it basically scores all the actions, if you will. And now what can you do? Should I just pick the first action? Should I just pick the best action? So it has given me a recommendation of actions, right? And the n number is decided by the knowledge which says these are the only actions you can take, and this guy has ranked ordered these actions. Should I just pick the first action? Some learning, right? So we have already learned a bunch of things. So I've played many games, so I know how to play chess now. But should I always pick the first action? No? Unless, you have to look to the future. So let's say all that knowledge, after looking into the future, has already been encoded in this, right? So, it depends on who I play with, who I want to win or lose. Right? It's not who I play with. It's really about, am I confident about this, right? So if I'm a grandmaster, and if this is my model, then definitely I should do this, right? So the idea is, really the question is, have you explored enough? And now there are three kinds of things you can do, three kinds of questions you can ask. You can say, given subject and predicate, what is the object? A question like this. Given subject and object, what is the predicate? Right? And the third question you can ask is the third one, which is given predicate and object, what is the subject? Right? So we understand that factoid question answering is now as simple as converting it into this language and creating answers from it. Right? Again, a very simple task. Now I want to go into two things, which is how can we do similarity and reasoning on top of these things. Now we all understand word embeddings, right? So we all know about word embeddings, and the basis of this is this notion that you shall know a word by the company it keeps. So the idea is skipgrams and all these models, all they do is they look at a word and look at the context and say if two words have same context, they must be similar, right? So that is what has led to a lot of research in word embeddings. But my hypothesis is that there is no such thing as language. So how can you learn word embeddings? What does it even mean? So let me question this a little bit and see what do these similarities actually mean. So what happens when you learn a word embedding? All the words in your dictionary are part of the same embedding space, right? All the words are part of the same embedding space. My question is that the right thing to do? Right? So let's look at some examples. Does it make sense to ask this question? What is the similarity between apple and eat, or Bangalore and likes, or Google and search? Linguistically, you can say Google is search and all that, but linguistically, these are two different things. What about this? Apple and red, Bangalore and progressive, Google is profitable. Does the notion of similarity even exist? I'm not even saying whether they are similar or not. All I'm asking is, does it even mean something? But you could compute these if you did your word embeddings, right? I can come up with a number and say, yeah, this is the similarity between apple and eat, because here is one vector, here is one vector, and you can do a dot product. But it doesn't mean anything, right? So there's something weird going on about embeddings in that way. What about this? Bangalore and Taj Mahal. Now both are nouns, right? Dog and aspirin, tree and Google. Right? What about apple and orange? What about Bangalore and Hyderabad? So which of these four is actually meaningful if you think about where we can compute similarity? Last one, right? Now, so that is the idea behind how do you compute similarity using knowledge and not using text, right? I don't want to get into that text and co-occurrence in this thing, but because it doesn't mean anything. So I can't measure similarity between verbs and nouns and adjectives. That doesn't mean anything. They have to belong to different spaces, if you will. Similarly, I can't do similarity between entities of two different types. Even if both are nouns, Bangalore is a noun, Taj Mahal is a noun, but I still can't do similarity because it doesn't mean anything. They are entities of different types. So it's not just about part of speech, it's about entity type, right? And here we can do because all these are entities of the same type, right? So that is where the embedding models breaks down, and therefore you want to talk about knowledge embeddings, which is how do we create embeddings from the knowledge graph directly, because there is no such thing as language. So the hypothesis I'm going to go with is you don't have to have a single embedding for everything. You have to have different embeddings for different things. So if you're thinking in an e-commerce environment, all my customers and all my products and all my reviews have to be in the same embedding? No, because these are three different types of entities. Think about different embeddings for each, and now think about how would you translate your word to vector ideas into this kind of thing, so you have different embeddings for different. So it doesn't even allow you to do this similarity, right, between this and this. Okay, so how do we compute this similarity? How do we compute these embeddings, right? So why do we know that aspirin and ibuprofen is even comparable? Because they are entities of the same type. But now I'm only given knowledge graph. I'm not given text data. So I cannot think about neighboring words and skipgram. How do I create similarity between these two? So what can I say is, any ideas? We do the same thing that we do with text, except now the idea of context is different, right? So we say, what does aspirin do? Aspirin is a node in a knowledge graph. It has a relationship with some other entities. This has a relationship with some other entities. And because of this, this is similar to this. So the idea of context in a knowledge graph can be thought of as, can you think about the similar context and then say these two are similar? Okay? And now I'm going to propose an alternate way of looking at this whole thing, which is you shall know an entity. There is no such thing as a word, right? So that doesn't mean anything. You shall know an entity by the company it keeps in the knowledge graph. Okay? So that's the new definition of what we can do in similarity. Let's make it a little harder. How do we know that Isaac Asimov and Arthur C. Clarke are similar? Pardon? Cipher, right? So if I traverse the knowledge graph and say this guy wrote these books, this guy wrote this book, and then this guy's book has a genre of science fiction, this guy has a genre of science fiction, therefore they are similar, right? So the idea of similarity now we understand, and this process that we went through, right, going from entities to states to entities to states, if you will, is what we are calling reasoning, right? So in a way we are using reasoning to actually compute similarities. Okay, so my favorite part, how do we do analogies? How do we think about, this became very popular when word vectors came about and we did king, queen versus men, women. So let's see how we do it, how we do analogies, right? How do we do it in our mind? What is thinking in this context? How do we know what is the answer here, right? Steve Jobs is to Apple, who is to Microsoft? And if I say Barack Obama is to what, Narendra Modi is to Vadnagar. Now I don't know how many people know, but this is his birthplace, right? And if I know that, then only if that edge and relationship is in my knowledge graph, then I can solve this, right? But the process of solving all these, how do we solve this given a knowledge graph, right? So I don't have embeddings yet. I'm not doing differences between word embeddings because there's no such thing as a word. So what do we do? These are all entities. They are related to each other. And let's see how do we solve it in our world, right? So how do we do this? What is going on in our minds? Right? So we say, what is the relationship between these two guys, right? Things. And then we say, okay, we run a query on a knowledge graph and says, what is the relationship or a predicate between this as subject, this as object, and it says founded, right? And then we say, okay, if I apply the same thing to this other predicate, which says who founded, because I got founded from here, and then I put this guy here, I'll get the answer. You understand how it is very simple. We don't have to apply large vector products and all that. We just do a very simple two-stage reasoning process to think about this. So again, Narendra Modi, predicate, you say born in, and then you get that. Okay? All right. So now let me talk about how do we create a new architecture of reasoning, right? So we've talked about deep learning and other things. These are great architectures. I'll show you a very simple idea on how do we build a reasoning engine that is very conducive to all these things we just talked about. So imagine you have three networks. One network is mapping subject-object to predicate. Another network is mapping subject-predicate to object. And all we are doing is a lookup on a knowledge graph, right? There's nothing special about these networks. These are not even networks. These are just lookup tables on hash maps. And now let's see how do we solve that problem. So if I put Steve Jobs as a subject and Apple as an object, this network is going to tell me founded. And then what happens? I take this guy back into these predicates, and then I put anything here. I put Mark Zuckerberg here, and it tells me Facebook. And if I put Microsoft here, it puts Bill Gates. Right? So the idea is this is how our associative reasoning kind of works, which is it goes through these three networks. And if I want to put a general structure, imagine I have a set of active entities in my mind and a set of active predicates in my mind. If I take these active entities and put them in these networks, nothing will happen. Well, this guy will do something. This guy will not do anything. This guy will not do anything. Okay? But when this guy does something, it will give me 10 minutes. So then what I can do, I can put it back here. So now this guy are going to generate the red lines and entities, and this guy is going to do this, and I can do this recursive process. Okay? So let me just summarize. So we have talked about two kinds of reasoning. One is a Markovian reasoning, and we think it is different, but it is not. Really, states and actions can be thought of as entities and predicates. And the real question we have to ask is it a problem, a prediction problem, or a reasoning problem? Okay, so I'll stop there and take any questions or. Thanks.
I've been watching artificial intelligence for about 40 years.
Wow.
So probably most of you, since most of you were alive. And it has always felt almost mature according to its practitioners. When I was 1, I was just begun. When I was 2, I was nearly new. When I was 3, I was hardly me. When I was 4, I was not much more. When I was 5, I was just alive. But now I am 6, I'm as clever as clever. And I think I'll be 6 forever and ever.
Yeah.
I make one prediction that in the 5th elephant in 20 years' time, let's call it the 25th elephant, all of this material will fit in the childhood stage. And just as an example of kinds of reasoning, you had the mathematical one of simple replacement rules. As a mathematician, that is not how I think. I look at x cubed minus y cubed. I look at x minus y, which I would like to divide by. I see that if x minus y is 0, then x cubed minus y cubed is 0. Therefore, there is a way of dividing it. And I don't remember the formula, like you said.
Yeah.
I know there must be an answer, so I do the division. The big thing about mathematics, it saves you on memory because there are systematic principles. I gave up physics because I had to learn too much, let alone history.
Yeah.
I could apply ideas, and I don't think you can really claim that this scheme is yet capturing idea thinking. It's doing an amazing amount. I'm not dissing it,
Yeah.
but it's not adult yet.
Yeah, that's it. Thank you.
Hi.
So there's a lot more, and yeah.
Excuse me. Yeah, just a quick question. How do you model induction or inference in your framework?
So the Bayesian reasoning does that for you, right? So if you look at how the graphical models work, they can go backward if you have to apply the Bayes theorem and keep going backward, or you can go forward by applying it in a different direction. So different types of reasoning require different types of framework. Like he's saying, mathematical reasoning needs even more than what we have talked about.
Yeah, hi. So I was just trying to draw parallels between prediction and reasoning, right? So in some sense, prediction is basically a search through the hypothesis space. Reasoning is a search through the state space.
No. So the reasoning is, think of reasoning also as a search in the hypothesis space, except the hypothesis is a sequence of actions now. Earlier, in prediction, the hypothesis is one prediction. Now, if you just transform it and say, what is the path?
Right.
And I say, now obviously the problem has become more complex, right? Many paths. But really, if you think in those hypothesis terms, then the hypothesis is different. I'm not looking for one action, but hopefully through a collection of actions, the path will be correct. And that is the hypothesis, not the action.
So I mean, is there a kind of way to kind of identify a certain problem as being a prediction problem versus a reasoning problem, or is it just a modeling choice?
Yes. No, it is not. It is not.
For example, I mean, taking the example of the knowledge graph, right? So people have tried to do kind of link prediction and all that, right? So, versus you could do reasoning, as you said.
Yes.
So is the difference that reasoning is more kind of deterministic versus link prediction being kind of a probabilistic approach?
Because there could be statistical reasons for saying, is this link should be there or not? Is it consistent with the rest of the knowledge or not? So you have all those are prediction problems. Whether the link should be there is a prediction problem.
Right.
But how to use a collection of links across the graph is not a prediction problem, because you're traversing a path, if you will, like on a map. So I'll give you an example. If you want to think about predicting churn of one customer, that's a prediction problem. But if you want to optimize the lifetime of a customer for yourself through a series of actions, it's a reasoning problem.
Sure.
So it's not a modeling choice. We only think well when we think of single actions. But we just need to now think that nothing is a single action. It all depends on a sequence.
Right. So even the notions of...
So I'll take more we can discuss outside. Next.
We have time for one more question.
Okay.
Hi, Shailesh. Excellent talk, as always. But when you talk about associative reasoning, right? So you're actually reasoning within a closed state space. So where do you put the bounds on how much of reasoning do you need to go into? For example, depth. So classic example is when we are surfing Wikipedia, we get lost in a sea of information. So what's the depth to which we go to when we do?
So again, there's a very big trade-off in AI, which is how long do you need to think about predicting the next action? And if you can think long enough, like if I sit for 200 days and think about my first move, I can make the optimal move. But then, I won't be able to play the game. So that trade-off about the quality of solution you get and the amount of exploration you have to do is always there. And we need to find a balance between these two.
Right. So my just follow-up question is, how do you do this exploration in an unknown space? So now...
So the big assumption here is the knowledge is complete. It's a closed world assumption. So that is somebody else's problem.
Thanks.
All right. Thank you, guys.